Chemistry students, it's time for some further discussion about aqueous solution type reactions. This subset will be discussing things about oxidation and reduction, how we're going to assign oxidation numbers or recognize these oxidation reduction reactions in more detail. And the second portion will give us more information about species oxidized and reduced, which things are oxidizing agents and reducing agents. Okay, when we're talking about oxidation and reduction reactions, aka redox, we are thinking about things that are literally transfers of electrons. You can take an anion and take away an electron from it, and it becomes less negative, such as A2 minus becomes A minus, or A minus, if you take away an electron from that, it becomes a neutral atom, and then the neutral atom, if you take away an electron from it, it becomes a cation. And the last one is if you take a cation of +1 and you remove an electron, it becomes a +2 cation. Examples of those are all oxidation processes. Reduction is the opposite of each of these. So oxidation is losing electrons, and reduction is gaining electrons. So in the reverse sense, those reactions would be reductions of those. There's 4 examples shown here. The example shown at the top of the screen, iron combining with oxygen to make iron 3 oxide, is clearly an oxidation reaction. And in the truest sense, adding oxygen is exactly the same thing as a very typical or simple example of what oxidation really is. So adding oxygen in the very simplest original context is oxidation. The opposite is also true. Reduction is shown at the bottom, where we take that iron 3 oxide and combine it with carbon to make iron, and that's one way of manufacturing iron and then having CO2 left over. The iron is losing oxygen in the literal sense here, and therefore it is being reduced to regular plain elemental iron. So adding oxygen is a simple definition of oxidation. Losing oxygen is another definition of its reverse, namely reduction. So all of these possibilities exist, and we will gradually get more acquainted with how we recognize and describe the different types of reactions taking place. So here's a reaction of magnesium burning in air, and combining with air, it's going to make magnesium oxide. If you recall an earlier definition from another part of the chapter, the combining of 2 elements to make a compound is clearly an oxidation process, where one element has to become a cation. In this case, the magnesium becomes a cation, and the other element becomes an anion. So some electrons have definitely been transferred in that process. So which part is oxidation, which part is reduction? So losing electrons, losing of 1 or more electrons is a definition of oxidation. And in this case, the magnesium is losing electrons to become a cation. So the magnesium loses electrons to become a magnesium cation. Reduction is the opposite then. The reduction is gaining 1 or more electrons. And so in this case, the oxygen atoms, or the oxygen, elemental oxygen, must be gaining electrons. So oxygen gains electrons, becoming oxide ions, and so oxygen is being reduced in this case. Now, if you think of it in an overall sense of being an electron transfer reaction, it still works, because the magnesium is losing electrons, the oxygen is gaining electrons, so it's transferring from one to the other. And if you put the 2 reactions together, because they've occurred simultaneously or concurrently, as you wish, then you recognize, hopefully, that the magnesium and the oxygen have a gain of electrons, but they're also lost. And so in the net process, the overall process then really doesn't include those electrons in the sum of the process. And then you're just considering that 2 magnesium atoms combine with an oxygen molecule to make a magnesium oxide. So there's both electrons gained and electrons lost in that process. Another example of an oxidation reduction reaction, might as well say redox, it's easier, is phosphorus combining with bromine. Elemental phosphorus reacts quite violently, in fact, and dramatically, to make phosphorus tribromide. Remember, that would be a molecular compound because it's two nonmetals combining. And this one is an example where you can recognize it's redox because two elements are converting to make a compound. So elemental substances combining to make a compound is going to be electron transfer, and we call that redox. Another example of reaction that's entirely more complex shows the permanganate anion, and its reaction with iron and acid to make manganese plus 2 ions and another form of ion as a result. And if you look at this closely, you can see that the iron begins as a plus 2 cation and turns into a plus 3 cation. And so, yes, electrons are being transferred. Now, the whole transfer here is a little bit obscured, and we'll learn as we go later how to explain that. But iron 2 has to loses an electron to become, so it's getting oxidized and becomes iron 3 in this process. So it's an electron transfer process. All right, next slide. Oops. So in order to recognize and carefully explain which things are being oxidized or reduced, it helps a lot to use oxidation numbers or oxidation states. I think I typically personally say oxidation numbers, but you'll see it noted both ways. It's a value that indicates whether the atom is neutral, electron rich, or electron poor. What is it? And so we have to get our heads around some rules that help us understand where the oxidation numbers are going. There are rules for assigning these oxidation numbers. So there's a set of them. Here goes. First one, any atom in its elemental state has an oxidation number of 0. So sodium, hydrogen, bromine, sulfur, neon. It doesn't matter if they're diatomic, such as the hydrogen and bromine. For any element, the oxidation number is always going to be 0. So don't think any harder. If you see something in its elemental form, that's where it is. That relates to the next rule, where we're talking about ions. The next rule tells us that an atom in a monatomic ion has an oxidation number identical to its charge. So the sodium ion is +1, the calcium ion is +2, the aluminum ion, it is +3, chloride ion -1, etc. So if the charge is equivalent to the oxidation number, then the same thing applies for a neutral atom that's not an ion. The neutral atom should have an oxidation number of 0. Ions have oxidation numbers identical to their charge. One way of thinking about these things is in terms of the periodic table. Metals are going to have positive oxidation numbers because they are more like cations in a general sense. Most of the time they'll have positive oxidation numbers. These are not foolproof, but good generalizations even so. And nonmetals are going to be more like anions and commonly will have negative oxidation numbers. But again, you'll find some oddities and variations as we go. Third rule, an atom in a polyatomic ion or in a molecular compound usually has the same oxidation number it has as if it's a monatomic ion. So when we see things in a polyatomic ion, we'll think in terms of what they typically would have by themselves in a monatomic ion. The more examples you see, the better. So think in terms of specific things in polyatomic ions, such as hydroxide. This example at the bottom of the screen is hydroxide. And hydroxide has an overall charge of -1. And so the oxidation number of hydrogen is an odd one, and we have to make sense of it. The oxidation number of hydrogen is going to be +1, except for certain examples where it's bonded to metals in binary compounds, such as this one. So this would be calcium. Let me write that carefully here, guys. Calcium hydride. It's a combination of a metal with a nonmetal, but not something we run into all the time, but you might. And so in this case, the oxidation number turns out to be -1. So most of the time, hydrogen is going to be +1, but there are exceptions when you put it in a funny thing, and this is called calcium hydride, and that is also a clue because hydride is going to be where you see hydrogen with a -1 oxidation state. So in hydroxide, hydrogen's +1, and the oxygen's -2, and the 2 together, the sum of these is going to be -1, which is equal to the charge. We haven't finished these rules yet, but that's what's coming. So the oxidation number of oxygen is typically going to be -2 most of the time, unless you run into it in a funny example such as peroxide. Peroxide is one of those anions that are more troublesome to us. It's going to have a different oxidation number. It's still negative, but it's -1. So in the case of water, on the left, we have oxygen with a -2 and hydrogen with a +1. Two of those, all of them add together to make a total molecule having overall charge of 0, and the total sum of the oxidation numbers is also 0. So add all these up, and we get the same value as we get for the charge on the molecule. For the hydrogen peroxide, the charge of the molecule is overall still 0. Peroxide is the odd one, though. And so peroxide, you have to use -1 for the charge on the oxygen. Hydrogen stays +1. It's normally going to be +1, unless it's in with a hydride, like a metal hydride. And so in this case, you add together the +1s for the hydrogens, -1s for the oxygens. You put it all together, and the overall sum of the oxidation numbers is going to also be the same as the charge. All right, so hydrogens +1, oxygens usually -2, halogens, that's the next generalization. They have usually an oxidation number of -1, according to what their charges typically will be. And so there's two examples here, hydrogen HCl. The charge is going to be 0 on the molecule. My tool isn't writing. Charge is 0, and for HCl, and the sum of the charges is also, or the sum of the oxidation numbers, oxidation states, adds up to 0 also. For this oxygen dichloride, the other curious example over here, oxygen dichloride, remember naming these things, folks? It's been a little while. We assume that the halogen is going to be -1, which works when we consider that oxygen is typically -2. And so the sum of the oxidation numbers is going to be 0, just like the charge on the molecule is also 0. So we expect those two numbers to be the same, should be the same. If not, we need to reevaluate. Okay, so hydrogen +1, oxygen -2, halogens -1. Good generalizations. So what I've alluded to in the previous examples is the sum of the oxidation numbers of all the atoms in a molecular ion is going to be equal to the charge on the molecular ion. So let's look at a couple where we're not sure what to do with some of these things, because not every atom has a generalization. Hydrogen and oxygen and halogens do, but here we have H2SO4, which is sulfuric acid. And sulfuric acid, we don't know what to do with sulfur right away, so we need to think about the parts we do know and figure them out. So 2 hydrogens, they're going to be a charge of or oxidation number +1. Assume they are. It's a good assumption. It works. And the oxygens, there's 4 of them, and they're each -2. And so we have to figure out what the sulfur is, because the whole compound needs to add up to 0 with all the oxidation numbers. So if you pay attention to the math, we have 2 plus something plus, oh, that would be -8 then, wouldn't it? So the last value is that we're adding an unknown value, and then -8, and it all has to add up to 0. So the charge on the sulfur is what remains. So the question mark is going to be what? Well, I've written this in a funny fashion. The question mark will be the value for sulfur, or 6, +6. So sulfur is going to be +6 in this example. Now, the dichromate ion. You don't like these ions, do you? They're unfamiliar. We don't use them often enough. But here's an example of where it comes up. The dichromate anion, if you will, because it is definitely negative. We have to decide what the charge or the oxidation state on chromium is. I keep saying charge because charge is a lot like oxidation state, but it's not exactly the same thing, because the whole entity has a charge of -2. And so we know there's 7 oxygens that have a -2 oxidation number, and there's 2 of chromium, and those have to add up to -2. So the chromiums, that was sulfur up here, the chromiums, 2 of them plus a -14 have to add up to -2. And so this has to be a total of 12. And so the 1 chromium has to be half of that. And shouldn't be too much math to hope you can see that it is going to be an oxidation state or oxidation number, either one, of +6 for the chromium. So a little bit of arithmetic, not a calculator exercise. Hopefully that makes sense. Okay, so in order to make sense of these, we should do some practice. What are the oxidation numbers of each element in this hydrogen carbonate anion? Well, a hydrogen carbonate anion, what should we do? So there's the formula, and we have to pay attention to each part that we know. Oxygen is going to be -2, but there's 3 of them. And there's hydrogen is +1. And so 3 times the -2 plus 1 for the hydrogen plus something else has to add up to -1, which is the charge on the anion. So what do we get for the oxidation number on the carbon? The carbon is what's left, so carbon has to be +4. In other words, -6 plus 1 plus 4 gives you -1. Another example, or set of examples, so there's 3 of them here, and if you dare to be brave, you can pause the recording and try them yourself and see if you can figure out where they're going to go. So let's do them in order, starting with sodium iodate. Iodate. Remember that anion. We forget these things sometimes. Iodate. Good to remember. All right, so what are we going to do with that one? Sodium is going to be the same as it were if a monatomic ion, namely +1 cation. The oxygen is going to be -2 because it will be. That's good, reliable generalization. And then the iodine is the one we have to figure out. So the iodine is going to be the difference between, or what remains to make it all add up to 0. So 3 times the oxygens is -6, right? Plus 1 plus something else has to add up to 0. Oh, I probably didn't put that. I shouldn't have. All right, I'll take it off the screen. And so the iodine has to be +5 to make it all add up to the sum of 0. So iodine turns out to be +5. So here's an example of halogens not being -1. It depends on what context you find them. Don't be too sure. So example number 2, same thing. Example number 2 has iodine heptafluoride, so it's 2 halogens. They can't both be -1 or it won't work out. So in this case, we're going to take the fluorine to be -1 because fluorine is going to be the same thing as it has for charges in anion. And fluorine is never going to be anything but -1 as an anion. And the iodine will be the one that doesn't have the same as its charge. And so 7 of something plus the iodine has to equal 0. So in this case, iodine is +7. In the example with the iodate, it was +5. So as you can see, they vary somewhat from one example to the next, what some of these elements turn out to be. Okay, so we have potassium dichromate for the 3rd example. Potassium dichromate is going to contain the dichromate ion, which, if you remember from a few slides back, we already discussed. But let's try it again just to make sure we're looking at the entire compound now. So in this case, the oxygen's -2, and there's 7 of them. The potassium is +1, the same thing it would be as if it were a simple monatomic ion, and potassium is always +1. It's quite reliable that way. But now we have to figure out what chromium is going to be. So 7 of the oxygens together makes -14 total charges. 2 times the +1 is +2. And 2 times something else has to make it all add up to 0. And so the remaining portion is what is left for the chromium, for 2 chromiums. And so it looks to me like it should be 12 divided by 2 or 6 for the chromium in this particular compound. I will conclude this recording here, and we'll go on to more examples of talking about oxidation and reduction reactions in the next recording. Good luck on your homework. I hope these things help you. Please be sure to ask lots of questions, and see you in class.